Hello, welcome to Special Maths Academy. In this video, we'll be looking at solution to the just concluded Special Maths contest. For this problem, to figure out the potential answer, we could consider special case like cyclic polygon or regular polygon, and that might give one of these options, but the issue here is the option E, which suggests that it's possible that perhaps there might be a convex polygon that is irregular that may not give the same value as a regular one, right? So this means we have to take this a bit more technically. So to see what the question really is asking about, let's give a sketch about the polygon. So let's say we have the first few points, vertices of the polygon. So let's say P1, P2, okay, so all the way to P12 and beyond, and we can go all around until we get back to P20, 22, and this will just be the same as P20, 23 and so on. So yeah, so we have 22 points. Now the angle of interest for I equal to 1, for instance, will be P1, P6, P11. So connect this with the line and also connect this. So this angle here is the angle of interest. So let's call this angle theta 6. Okay, so this for theta 6. We do this 22 times. That means you're going to have theta 7, theta 8 and so on. So for example, if I use a different color here, just a moment. Okay, so for theta 7 it's going to look like this. Theta 7. So we are to add all these angles together. So in fact, if we complete this figure, it's going to be one huge star polygon. So in particular, it's going to be a 20, 22, 5 star polygon. So star polygon is a polygon whereby we connect. So we have these points. Let's say we call this N, we call this M. So we have N points in a convex form, and then we connect edges after M points each. So from P1 we jump to P6, we connect. From P6 we jump to P11, connect. Then we add 5 to that. So in this case, M is equal to 5. So that's going to create some kind of polygon, because at the end of the day we're going to end up going back to the origin at some point, and we'll do that for every point. So for star polygon, there's a formula for this, so we're just going to quickly derive it, and then we'll see that the answer is always going to be fixed, and also we'll find out exactly what the answer should look like. So to do this, first of all, I'll just quickly point out that if we focus on, say, P1, P6, for example, we'll have M minus 1 other points, in this case 4 other points here. If we connect P2 to P7, we expect it to indeed cross this line at some point because of the convexity. That's because P1, P6 divides the polygon into two parts, where P2 up to P5 lies on one side, and then P7 down to P20, 22 will lie on the other side. So drawing that line segment is going to intersect because of convexity. Okay, so also we can try to give this some kind of direction or bearing or some kind of vector as well. So if we do that for each of this line, whereby it's pointing to the next point, so Px will be pointing to Px plus 5. Okay, so if we do this, we'll see that the slope of all these lines will gradually change one after the other. So let's call these lines so this particular line, let's call it Lx. So for example, this will be L1, the red one here will be L2, and will continue like that. This other black one, P6 here, will be L3, and L6 rather, and then L7, and so on. So the idea here is that the slope is going to be changing gradually, because we know they are going to intersect. So from there we can see that there's going to be some small angle at each of these points. It's going to keep changing gradually. So what we're going to do now is we're going to just construct another diagram based on ideas from vectors. So we'll start with some origin, let's say O. So what we're going to do now is we're going to pick each of those lines, which are actually vectors, and we're going to apply them to O individually. So for L1, it's going to be parallel to that, so I'm just going to draw it in proportion. So this is L1. It's going to go to some other point, which I will just call Q1. Okay. If we look at L2, that's the red one. So let me make use of the red angle. Then we're going to have with a slightly lower slope. It's going to look like this. So parallel. So in this case, OQ2 will parallel to P2, P7. Right. So this will be the same vector as L2. Okay, so we can actually do the same for other lines as well. So we'll have P4, P5, and so on. So just briefly, let me quickly confirm why we expect them to be gradually going downwards. So let's say we have some Px going to Px plus 5. And then we also have the next one, Px plus 1, going to the next one after Px plus 5, Px plus 6. Then if we connect Px plus 1 and Px plus 5, we see that that is going to have a slightly lower slope than Lx, but higher slope than Lx plus 1. So that's because we can draw a parallel line here. And then not necessarily going to Px plus 6, and then we see why this new line is lower than Lx but higher than Lx plus 1. So ultimately Lx plus 1 is lower than Lx. Okay, so we just continue like this, and it's going to go round, all around, and we're only going to have it going round once, because if you just pay attention, you see that we gradually turn it around until we have the full circle and get back to Q1 for the first time, right? So this means that just before this we must have Q20, 22, and so on. So lots of lines like that. Okay, so particularly I'm going to be interested in here we can see that the lengths are not too important, because we're going to be looking more about the angles. Let's look at Q6. Okay, so Q6 now, this line will correspond with L6, and theta 6, which is an angle of interest. We want to see how this compares with these other angles now. So let's call these angles, let's say this one is alpha 1, this will be alpha 2. So we have some other ones in between. I'm just going to quickly draw them. So that's L4 and L5. L5, L4. So we have alpha 3, alpha 4, alpha 5. Okay, so there's just a nice geometry that's going to happen here. We have, I'm just using theta 6 as an example. It's not, 6 is not special here. So we have something like this, where this is L1, L6. But we now have another diagram like this, where this is L1, L6. So from parallel lines, we see that we can extend this, and this angle will have to be theta 6. So whatever is here must be 180 degrees minus theta 6. And this total angle here is going to be equal to alpha 1 plus alpha 2 plus alpha 5. Or we can make a theta 6 subject and say this is 180 minus alpha 1 plus all the way to alpha 5. So this is what we actually have, and then we just need to sum this for all 2022 numbers, and then we're good to go. But we keep in mind that alpha 1 plus up to alpha 2022 will just be a full circle, so that's 360. Okay, so what we're going to do now is we write this formula in a general form. So theta I plus 5 will be 180 minus alpha I plus 1 all the way to alpha I plus 4. This is for all I. So we're just going to sum over I from 1 to 2022, and then we'll see what we get. So since we have things in circles, on one hand we have what we are looking for, this sum. On the other hand, we have 2022 times 180. So this can be generalized, but I'm just going to go specific to our problem. And then minus, for each of these alpha i's, we are summing over all 2022 different values. So it's just going to still be the same as the sum, which is going to be 360. That will be a full circle each time. So this will be 360 times 5. So this will be 222 times 2 minus 2 times 5 times 180 degrees. So the more general formula will be n minus 2m times 180 degrees. Okay, and then once we simplify this, we are good to go. Okay, so this will just be, in our case, 2022 minus 10, so that's 2012 times 180. So let's see which of the options. This will be 2012 times 180. Okay, so we have this is not correct. Yeah, so this will be option A, which is just another form for this. Divide by 2 and multiply by 2. So that's going to work out. Yeah, so the correct option is A. Alright, I hope you enjoyed this. I'll see you sometime later. Thanks for being part of this. Bye.